As we live through the sixth great mass extinction made from the foundation of profit above all else, we, as scientists, must look to the other 5 extinctions to get an increasingly spot-on prediction of where we're going next and how best to avoid the harshest sentences imposed by said extinction, besides of course just doing the right thing. Each mass extinction has a certain air of mystery to them, with some leaving behind a more thorough record to read than others. One mass extinction, which occurred between the Triassic and Jurassic periods, seemed to kill off anything that was not insulated against cool climates, and new evidence uncovers implications that the dinosaurs sailed through the extinction due to an ancestral coat of feathers. The latest stretch of the Triassic period and earliest chunk of the Jurassic, about 201.36 million years ago, is one of the few slices of time in Earth's long history during which there is no evidence of glacial ice sheets at the poles. According to the fossil record, which is admittedly faulty in many respects, forests were present all across the ancient supercontinent of Pangaea, from the North Pole to the southern latitudes, as far as the land reached and the eye could see. This is odd, for there were even patches of polar ice during some of the hottest times in Earth's history, like the hothouse worlds of the Carboniferous and Permian, though there were certainly some periods here that saw a melting of much of this ice. Though there may have been many other contributing factors as to why there was such low pole ice during the late Triassic and early Jurassic, the leading hypothesis here is that Earth was in this hothouse state due to high levels of carbon dioxide in the atmosphere, specifically between 1,000 to 6,000 parts per million, which are the highest levels of CO2 in the last 420 million years of Earth history. This is all a bit odd because the evidence is funky. Paleoclimate models of this period of time have shown that there definitely should have been freezing winter temperatures at the high latitudes, but empirical evidence from the rock and fossil records is lacking in the freezy department.
What killed the dinosaurs? The Ice Age!
Just despite this lack of hard empirical info that proves what the models have already found, a new paper was just published in Science Advances by a team of 10 researchers led by Paul Olsen, which provides that empirical evidence. It shows that, despite the extraordinarily high levels of CO2, freezing winter temps did weed their tepid, crispy fingers into the high latitudes of Pangaea. That evidence being in the form of lake ice-rafted debris found in early Mesozoic-aged strata of the Jungar Basin of northwestern China. Historically, the dinosaurs have been viewed as animals that thrived in the mild, warm, early Mesozoic climates. The results of this new research indicate they endured freezing temperatures early on in their evolution. The new paper argues that the rich plant resources of these cold, high-latitude regions were a key to the survival of early fern-munching dinos. It was the insulated dinosaurs who thrived in these regions that were able to sail through the mass extinction, volcanic winters, and high CO2 levels of the Triassic-Jurassic mass extinction that killed off anything that was not insulated. How did the team get to this conclusion? It's all in the rocks, baby! The rocks in which the team found their evidence, the late Triassic to early Jurassic rock layers of the Jungar Basin of northwestern China, were originally deposited north of the Arctic Circle at about 71 degrees north at the time. These rocks were cyclical, coal-bearing, fluvial, and lacustrine rocks belonging to the Huangshangjie, Aojigao, Badawan, and Songonghe formations. Cyclical seems self-explanatory, but coal-bearing indicates humid climates, high temperatures, and lots of swamps and vegetation. Fluvial means rivers, so lots of rivers were here. Lacustrine means lakes, so lots of lakes here. One might even say it was a land of lakes. The lakes and rivers fit nicely with the coal. The boundary between the late Triassic and early Jurassic occurs at the bottom of the Baaaby Formation. So, like sort of near the middle of that long list of formations I listed earlier. There are multiple occurrences of a specific type of sediment bed that occurs both in the Baaaby boundary and the Huangshangjie and Aojigao formations. This means the sort of environment these beds indicate occurred over very long periods of time. These beds are made up of thin, dark gray to black, fine-grained, lake-originated mudstones with a bunch of dispersed lithic grains, or sand-sized particles of other types of rocks rather than the usual quartz-derived sands. These beds have fossils in them, like bivalves, shrimps, fish bits, and tetrapod pieces. The researchers used a type of mathematical morphology called granulometry to compute the size distribution of grains of binary images. Here, those binary images being itty-bitty grains of sands and stuff. These tests found that the grains were bimodal, so two modes, or a graph like this. In discussions of ocean-derived rock layers, this type of grain size distribution is indicative of ice-rafted debris. So, the weird grains are picked up by ice on the beach when the surface freezes, and then the ice takes that debris out to deeper waters, and the ice melts, dropping off its unique payload to the bottom of the deep parts where it would not naturally occur. Well, all of this is happening naturally, but you get what I mean. This sort of phenomenon usually occurs in marine sediments when ocean ice forms, but it even happens in chunks of the ocean where glaciers don't really have much of an effect. In other words, this phenomenon occurs both in places that are under the stress of glaciers and places where there are no glaciers but where there is ice that forms on the water's surface. On average, all this stuff tends to happen in a seasonal manner, as the ice has to melt completely when it moves out to deeper depths to drop off its gritty cargo. There are other ways in which the sediment can make its way from the contact between water and land to the depths of the water body, but they don't leave behind the same kind of evidence as the ice-rafted stuff. Like with everything in life, the situation is more complex than it seems. Turns out, not all sediments from lakes with seasonal ice have that lake ice-rafted debris. Why? Don't know. A precise explanation remains unclear. Instead of trying to figure this out on top of everything else they're doing, the team made sure to illustrate examples of sediment cores from bodies of water with and without lake ice-rafted debris, both of which exhibit seasonal freezing. This was to compare both modern analogs to what is seen in the Jungar Basin lakebed deposits that show similar variations in the lake ice-rafted debris. Here comes the dinosaurs to bring back your attention. Shallow water, siltstone, and sandstone beds from all three of the ice raft debris formations in this study also preserve the fossilized trackways of dinosaurs. These footprints show that dinosaurs were present here at these Arctic latitudes, which are associated with freezing winter temperatures. This physical proof aligns precisely with climate models conducted on this region, which state these latitudes would have had such climate fluctuations. Past fossil research only expected warm climates. Models expected the possibility of seasonally cold climates. And the new research found that there actually was physical evidence that this region experienced seasonally cold climates cool enough to produce ice. The research was unable to fully rule out the possibility that there were permanent bodies of ice here at the time, but the researchers were not attempting to prove that, since that is not what their data specifically proves. The ephemeral or seasonal nature of these cold climates and ice formations is proven by other layers of rocks that are missing the lake ice-rafted debris, which means there were warm intervals punctuated by cooler ones.
Now eventually you do plan to have dinosaurs on your dinosaur tour, right? Hello? Hello? Yes?
I really hate that man.
The freezing temperatures now confirmed, at least seasonally, in the high latitudes of the Triassic-Jurassic boundary have large implications for the paleoecology and distribution of animals at the time and place. Though technically an animal could walk from pole to pole thanks to the supercontinent, animal communities were still divided latitudinally and of course due to geography, like mountains, rivers, etc. This was especially marked with herbivorous dinosaurs. Unlike today, the highest biodiversity was found in the mid-latitudes. The oldest dinosaurs come from the Carnian age of the late Triassic epoch, so about 237 to 227 million years ago, and in the Ischigualasto Formation of Argentina, which was at 48 degrees south. By the middle and end of this age, the Carnian age, 215 million years ago, large, 5 to 10 meters, 16 to 32 foot herbivorous sauropods, what you may remember used to be called prosauropods, were quite common at the mid-latitudes, 24 to 60 degrees, on both hemispheres. Despite this, animal assemblages from coal-bearing high latitudes are pretty much huge mystery caches. As a contrast, the low-latitude regions of Pangaea seemed to have been rather rare in dinosaurian fauna. The large herbivorous dinosaurs were rare except for the mid-latitudes. What animals dominated those lower latitudes? Everything that wasn't a dinosaur or related. The phytosaurs, atosaurs, and other reptilian members of the Pseudosuchia. Small carnivorous dinosaurs were present in these Pseudosuchian-dominated low-lat communities, but were rather minor players. Even the giant temnospondyl amphibians differed markedly between low and mid-latitude communities. Therefore, I think it can be concluded that large herbivorous dinosaurs were restricted to higher latitudes. Okay, weird. Animals were not the only ones restricted to certain zones of Pangaea. Plants from this time show a strong zonation through the different latitudes. For example, the equatorial tropics were dominated by conifers, seed ferns, and ferns, especially during the wet seasons. Many living members of these groups are freeze-intolerant, correlating to their ancient biogeography. In contrast, the semi-arid tropics and subtropics had low diversity in their plant communities and were dominated pretty much only by conifers. The mid-latitudes had a higher plant diversity. For example, the high-latitude areas of what is now northwestern China had abundant deciduous, large-leafed conifers, as well as ginkgos and trees sheathed in wood with well-developed growth rings. This is all consistent with a cool to cold winter climate with some warmer interludes. The plants themselves are not the only ones to corroborate the climate. Pollen and spores prove it too. Spores and pollen show strong zonation from one rock deposit to another. Despite the seeming lack of geographic barriers, on account of all the continents being joined, there was clearly a lot of biological ones, with communities zoned out according to latitudes. How did the dinos do it? Why did everything else die? The team used what is called a generalized phylogenetic bracket approach to infer different biological traits to different extinct animal groups to see what it was that was keeping these animals separate from one another and why some sailed through the extinction and others did not. Through their analysis, the team found that all modern reptiles are what's termed eurycotelic. This just means they have the adaptation for conserving water by synthesizing and excreting uric acid, which is a component of urine. This is why most reptile poops have a big chalky white component to them. Their bodies take all the water out and squish out the pure uric acid. This adaptation was likely present in the very earliest dinosaurs, but more importantly, was definitely present in the non-dino, non-archosaur members of the clade Archosauriformes, the mainland animals of the low latitudes. This excretory adaptation is great for hot, water-stressed environments, which made up most of the low latitudes. Next, the team looked at integument, all the stuff on the outside of the body, like skin, scales, hair, or feathers. Based on phylogenetic bracketing, feathers are ancestral to dinosaurs. If we wanted to be all-inclusive, this sort of covering may be ancestral to the Avemetatarsalia or Ornithodira group as well, since pterosaurs also had a form of feathery coating. This has been hypothesized despite a bunch of dinosaurs preserving only scaly skin, because there are members from the theropod group and Ornithischian group that have direct evidence of feathers. If feather impressions were only found with theropod dinosaurs, you could reasonably assume they originated with that group, since they occur in at least 3 Ornithischians, Psittacosaurus, Culindrodromeus, and Tianyulong, as well as a ton of theropods. They probably originate somewhere in the family tree when they shared a common ancestor. If pterosaurs, the most closely related group of archosaurs, had feathers, then surely the whole feather thing happened when the pterosaurs and the dinosaurs shared a common ancestor and were then lost in different families due to whatever environmental pressures. These physiological and anatomical characteristics correlate with geographical regions during the Triassic. The research team therefore infer that large herbivorous dinosaurs could not compete with the herbivorous pseudosuchians of the tropics and were mostly restricted to the colder climates. The extreme climates of the tropics suited the slower metabolism, arid adaptations, and lack of thermal insulation of the pseudosuchians over the adaptations of the early herbivorous dinosaurs. This also meant that the pseudosuchians of the tropics could not get as big as the dinosaurs. In contrast, the herbivorous pseudosuchians could not cope with the climates of mid to high latitudes where early sauropod dinos thrived. The integument of these early longnecks is unknown, but the integument of the more advanced sauropods is unequivocally primarily scaly. That being said, the early sauropodomorph dinosaurs are predicted to have some sort of thermal insulation, like protofeathers, according to this study. Since they usually didn't get that big compared to their later cousins, this is not implausible. This proto-feathery coating would have allowed these early vegisaurs to take full advantage of the more stable plant life of the high latitudes. What killed the Crocs? Now that I have thoroughly gone through the hows and whys that dinos survived the mass extinction between the Triassic and Jurassic periods, and why everything that was not insulated did not, why and how did the extinction happen in the first place? Like with most extinctions, there's more than one reason. So, prior to the extinction, atmospheric carbon dioxide was high. It was high during most of the start of the Mesozoic era, with upwards of 2,000 parts per million. For comparison, today's atmosphere has about 400 parts per million CO2, though to be fair, it's increasing with our inaction. Despite the high levels of atmospheric CO2, there was a sharp decline during the very latest stage of the late Triassic epoch, a time known as the Rhaetian stage, 205 to 201 million years ago, seeing a decline to lower than 2,000 parts per million. This was right before the extinction. This decrease in CO2 saw a decrease in ocean temperatures and, assumedly, a small decrease in global temperatures. This also saw an increase in dinosaurs and dinosaur body size in the tropics, but not in diversity, with just theropods having a presence. Then came the volcanism. It was near the end of the Rhaetian stage when the Central Atlantic Magmatic Province erupted and erupted and erupted. In fact, the whole province saw 4 major eruption pulses lasting 600,000 years each. The main area of eruptions was in the center of Pangaea, so parts of its aftermath are found in the Americas, Africa, and some bits of Eurasia today. These pulsed eruptions saw a doubling to tripling of atmospheric CO2, which may have resulted in an increase in global temperatures anywhere between 3 and 5 degrees Celsius, but may have been even higher. There are some paradoxical stuff going on here. The evidence clearly shows that abrupt increases in CO2 killed off a ton of marine organisms from ocean acidification and anoxia. Something, I should point out, is happening right now to our own oceans. Despite the clear evidence of what was happening in the high seas, what evidence there is of what was happening on land is at odds with the oceanic apocalypse. It seems to be at odds with very high volcanic CO2. With what is seen in the oceans at this time, one might expect to see evidence of mid to high latitude animals moving towards the poles where things were cooler. I mean, this is seen in some plants. On the contrary, the evidence all points to high-latitude animal communities surviving through the extinction and migrating towards the tropics. Especially notable with those early sauropods. They only start to appear in North American rocks at the extinction and after it. All of this is more consistent with volcanic winters, rather than volcanism-induced global meltdowns. So, what are volcanic winters? Besides what one might be able to deduce from the term, volcanic winters refers to devastating cooling caused by reflection of sunlight radiation off of volcanic sulfur aerosols. In order to have a global catastrophe as big as the Triassic-Jurassic extinction from this cooling, you need a lot of those aerosols. The Central Atlantic Magmatic Province was more than big enough and lasted more than long enough to fill the atmosphere with cooling aerosols. This even happened over long cycles, which fits into how enough of that stuff could stay around long enough to cool the planet. There is other evidence for this global cooling. Plants from the time show damage from increased sulfur aerosols. There is also an increase in plant species adapted to low light conditions at this time. These volcanic winters, occurring in the 1 million years from the latest Triassic to earliest Jurassic, were extreme and lasted a decade or more each. Individual lava flows from the Central Atlantic Magmatic Province were thousands of cubic kilometers in volume. Imagine that. Decades-long periods of volcanic eruptions, day in, day out, lava spews from the center of the continent. It would be like Yellowstone finally blowing its top, but continually oozing lava and belching noxious gas and chemicals for as long as some people have lived. Well, it would be like that, except the eruptions from the Central Atlantic Magmatic Province were 2 or more orders of magnitude larger than any historical eruptions ever. Thus, even if a single eruption caused saturation in the atmosphere of aerosols and then it dissipated, it would not end this time because the eruptions straddled the equator and the continents were stitched together as one. Had this volcanism occurred at a different time, perhaps the series of events that led to us would have been very different. Sustained temperature drops of 10 degrees Celsius or 50 degrees Fahrenheit were possible, which would have caused multiple events of tropical freezing, which is somewhat similar to the much shorter-term effects of the KPG impact 66 million years ago. From their discovery, the dinosaurs have always been conceptually associated with tropical or warm climates. But this goes against what we now know of them and their evolution. On top of later forms being found in Arctic regions, they seem to have been capable of surviving in cool climates since they first started to diverge from other archosaurs. The only non-insulated archosaurs to survive the Triassic-Jurassic extinction were small forms that could hibernate in burrows to wait out the cold, as has been suggested of many small animals for the KPG extinction, and may also have been the case for the end Permian mass extinction. In contrast to the orca-sized phytosaurs and wide-gauged atosaurs, the true dinosaurs didn't seem to face much of an extinction during this time. In fact, some underwent an expansion in size and geographic range. The early sauropods, which were originally restricted to the cool latitudes, then spread throughout the globe and began to reach some of their zenith sizes. The ornithischians started to pop up, and the maximum size for theropod dinosaurs increased by 20%, a near doubling of mass. A foreshadowing of greatness yet to come. For more interesting stories about nature, the history of life, or what goes bump in the night, subscribe, hit the bell icon for updates, like this video, and drop a comment in the comment section below. Thanks for watching. Special thanks to my elephant tier patrons: Arda Bayer, Biotiverse, Christoph Hubinger, Dinosaur, Isaiah Garza, P.A. Brew News, Ray, Rudy Redgrave, Smiling Walrus. And another thanks to my Tyrannosaurus tier patrons: Iberospinus, Iron Bladesman, Swaffles is Weird, Teeny Dragator, The Dogman,